I'm going to spend the time that I have telling you about what was really just an absolutely soul-crushing experience for me as a scientist. So here's the story. I am by temperament and training a physicist. I got my PhD at the University of Washington at this small town across the water. You may have heard of it over there. What's that place called? Seattle, right? And physics has had for centuries a really remarkable tradition of taking all the diversity of stuff that we see in nature, in the physical universe, and trying to explain it in a smaller and smaller and smaller set of ideas. It's sort of a reductionist approach, where you take all the materials that you see around you, the chairs that you're sitting on, all the sort of chemistry that we see, and you can express all that in the periodic table. And that can be understood in terms of electrons around atoms and shell structure. And then physicists said, well, wait a minute, actually, all those things in the periodic table are just made out of neutrons, protons, and electrons, and the rules of quantum mechanics dictate how the periodic table works. And furthermore, that handful of objects interact with each other with a particular set of forces, like electricity and magnetism, except guess what? They're actually pulled together into a single force called electromagnetism. They're nuclear forces, and there's just been this really remarkable intellectual tradition of having a more and more and more economical set of ideas to explain what we see. And when I was a graduate student, was a heyday of that reductionist philosophy in physics, and I completely bought into it. Hook, line, and sinker. I thought, oh man, this is so cool, you know? And the ultimate long-term goal of that program was to say, there's one mathematically beautiful theory of everything, and you can write it down in one line on the blackboard, and maybe it has a few sort of characteristic numbers like the mass of the electron and the charge of the electron, but you know, with kind of this many numbers and one beautiful equation, we should be able to explain all of physical reality. So is that a gorgeous program or what? Yeah. Oh yeah, big time, right? So that was the whole program, and along the way we've had a number of really intellectually revolutionary ideas. So one of them was quantum mechanics. In sort of the 1920s, people understood that there are discrete energy levels and the universe is governed by probabilistic rules and not deterministic things that I don't have time to tell you about. But quantum mechanics, right here, here's quantum mechanics. One of the big ideas in modern physics. Completely revolutionized the way we think about things. The second big revolution was general relativity. Understanding gravity is actually bending of space and time. And those two have a hard time being unified. One of the big sort of challenges in modern physics is to reconcile quantum mechanics and gravity. You with me so far? So three big ideas. Big idea number one is we're striving after the theory of everything. Intellectual revolution number one is quantum mechanics. Intellectual revolution number two was general relativity. It turns out that if you embrace quantum mechanics, and I hope there aren't any quantum mechanical skeptics in the room that will buy into quantum mechanics here. If you take quantum mechanics and say, well, let's think about what happens if we have just an empty cubic foot of the universe. Just a cubic foot of vacuum, empty space. So, from the perspective of Isaac Newton in classical physics, the idea of empty space is a really easy idea. Just reach in and take out all the billiard balls, take out all the inclined planes, take out all the simple stuff. And when you've taken everything out, what's left is empty space, and that's the vacuum. So far, so good? Yeah. Quantum mechanically, though, the vacuum is a really complicated thing, because it turns out it's this seething turmoil of particles and antiparticles spontaneously sparking into creation and then annihilating again. And you should think of it as this kind of seething foam of stuff. And that was all fine and good until the cosmology people came along and said, well, wait a minute now. If we got this great big seething turmoil of quantum mechanical vacuum and general relativity sitting over here, it turns out that that energy content in the vacuum should have a tangible and measurable impact. You should actually be able to detect this seething, churning quantum mechanical vacuum. So how might you do that? I'm so glad you asked. Here's the answer. If I took 1 cubic foot of seething quantum mechanical vacuum here and put it next to another cubic foot right here, there's actually a gravitational interaction between them. And we're all used to gravity being an attractive force, but it actually turns out that between those two pieces of quantum mechanical turmoil, the gravitational force is actually repulsive. It's anti-gravity. So far, so good? I only have 12 minutes. I got to do this really fast. So, when I returned to the University of Washington as a faculty member, me and my good buddy Craig Hogan got worrying about the quantum mechanical nature of the vacuum. And we started thinking, what experiments can you do? Because physics is not philosophy. You do experiments to figure out the way the world works. What experiments can you do to tell what's going on here? And it turns out that what you really need is just a gargantuan amount of empty space that's dominated by the vacuum, where there's not much mass. And about the only way to do that is to look out into the universe, which is predominantly empty, and ask, can you do some kind of measurement to see what's going on here in terms of the impact of this vacuum on the expansion of the universe? So, in the 1920s, one of the revolutions in cosmology, which is the study of the universe on the largest scale, was the recognition that the universe is expanding. Edwin Hubble, recessional velocities, galaxies, redshifts, all that stuff. So we've known since the 20s that the universe has been getting bigger and bigger and bigger and bigger. So why is it hard to find parking? I don't know. And that history of cosmic expansion is actually sort of a balancing act between the amount of matter that it has trying to hold things together and this pressure of the quantum mechanical vacuum pushing it apart. So we joined a team of astronomers, because I was only kind of a sort of pretend astronomer back then, now I'm like a real one. And we joined a team of astronomers, two groups embarked on trying to make this measurement of, let's measure not just that the universe is expanding, but how much is that expansion slowing down? Because that's a way to, that's a method to kind of weigh the average mass density of the universe, because that matter density slows down this expansion. So those two groups of astronomers were in healthy intellectual competition. And they both, pretty much in the same year, stumbled upon what was a really unexpected result, which was that the universe is not slowing down, but rather the expansion is going faster and faster and faster and faster, and the universe is just blowing itself apart. The consequence of that is that people really interpret that as really the effect of this vacuum, emptiness, quantum mechanical stuff governing the expansion history of the universe. So it wouldn't have been so bad if it weren't for the fact that the intellectual community of physics has not only people who do experiments, but there are these really smart folks called theoreticians, and they live on the top floor of the physics building. So if you're like sort of, a six-pack duct tape experimental physics guy like me who solders wires together and makes things work, you make a pilgrimage up to the top floor of the physics building. So you put on your oxygen mask, and you go past the graduate students, and you go up the stairs past the postdocs, and you go up to these theoreticians that sit on the top floor, and you say, you guys are really smart. Do me a favor. Would you just calculate how much this quantum mechanical turbulence should affect the expansion of the universe? And they say, no problem. Let me just have a latte. And then they go to the blackboard and they write a bunch of stuff down that you don't understand. You go, oh yeah, very interesting. And at the end of the day, they say, well, okay, so we've done this calculation, and the answer is that in some sort of natural set of units where we would weigh the universe, that the answer is that this vacuum effect should be 10 to the 120th, which is a 1 and 120 zeros. That's like a really big number, okay? It's so big that if their calculation were correct, the universe would have blown itself apart in the first blink of an eye after it happened after the Big Bang. But these theoreticians, I said they're really smart, they're not stupid people. So they look at that result and they say, well, that can't be right. so it's 0. And you say, well, how did it get to be 0? And they say, well, you know, this tooth fairy jumps out of the closet, and for every process there's an anti-process, and they completely, exactly cancel each other to 120 significant figures. And you say, really? And they say, absolutely, there's no question, because that first number is the most wrong prediction in the history of all of physics. We wouldn't be here talking about it if that were true, therefore it must be wrong. So wrong that the only other natural value is 0. And they were so absolutely convinced of their being right that that was taken as gospel, effectively. Okay? And then me and my buddies and another group went and measured it, and the end result was that the answer is 0.7. So I'm not a mathematician, but I'm here to tell you that 0.7 is not 0, and it's not 10 to the 120th, which were the only plausible results that people could possibly understand. So this is the oops part. So, I mean, the cool thing about discovering the accelerating expansion of the universe is that they handed Nobel Prizes to the leaders of our teams, and we got to go to Stockholm and have dinner with the King of Sweden and 1,000 of his closest friends. And the consequence intellectually, though, has been really quite earth-shaking, because it has really rattled the foundation of that intellectual tradition of reductionism, of thinking that, of the just intellectual arrogance of thinking that there's some beautiful equation that describes all of reality. And it has become, I think, for me at least, here's the soul-crushing part, is having grown up as a physicist who really believed that party line, and I still do actually, because we're a product of our training. There's now become this sort of turning point where young scientists say, that's ridiculous. Why did you guys ever think it would work that way? In fact, the universe that we inhabit is a pure accident. That actually universes are being created all over the place all the time, and only a very tiny sliver of those multiverses actually survive to grow stars and grow planets and grow people, and actually the physical reality that we see around us is simply a consequence of that selection effect. And it is utterly accidental. There is no profound truth, just deal with it. And there's this huge generational gap where people of my age with gray hair who have this sort of alternative metaphysical philosophy on how the world ought to be, absolutely abhor and detest that way of thinking about things. Because it undermines what we spend our entire life doing, right? That's a bad thing. So that's the oops part, which is, how can it be that when we went after this thing for completely good intentions, this is the law of unintended consequences writ large, you go do an experiment that you think is going to be a good thing, and find out that you have undermined your entire intellectual framework. So, so that brings us around to this project called LSST that's brought a bunch of us to town here this week. So LSST is a big telescope project that's the nation's top priority for the coming decade for ground-based astronomy. It's going to build a mirror that goes pretty much from that wall over here to somewhere over here somewhere, a 3.5 gigapixel camera, 15 terabytes of data per night. And one of the primary objectives of that instrument is to try to get to the bottom of what's going on with this accelerating universe and this stuff that we call dark energy that's dominating cosmic expansion. So we all look forward to the results from that project, and my colleagues are going to share with you some of their stories about this endeavor, and just thanks again for coming tonight.